Hello again, I am Xavi and we will continue with a second set of dynamical VAEs. So after the deep Kalman filter and the stochastic neural network, we will go through the variational recurrent neural network and a few other DVAEs in more or less detail. Variational recurrent neural networks are quite different from DKF and STORN in the sense that they are the most complete DVAE in terms of dependencies. So you can see here on the upper right of the slide how all possible dependencies are implemented in VRNN. So in a way, ZT depends on all previous variables, and XT depends on all previous variables as well as ZT. This means that when we decompose the joint probability of the whole sequence of observations and latent code, which is the first equation, we have all possible dependencies here in X and in the distribution of Z. Of course, the parameters of these distributions are computed with certain deep architecture. In particular, we assume that both the distribution of the latent code and of the observation are Gaussian distributions. The main difference is that the mean and covariance of the latent code depends on HT, which encodes all the previous information, and the mean and covariance of the observation depends on HT, the very same HT, as well as on ZT. It is quite clear from the generative model in what we call developed form. So here you can see HT, which is the recurrent hidden state, which is used to generate ZT, and also XT that exploits as well the information of ZT. So this is the graphical representation of the equations of the second and third equation. As we said many times, this is an implementation choice. We could have implemented the graphical model in the first diagram in a different way, but the authors of the variational recurrent neural network chose to implement the method in this way. This means sharing one recurrent variable to generate both Z and X. When it comes to the inference model, the posterior distribution of the latent code in the original paper is approximated by a sequence of posterior distributions in which each posterior distribution Z of ZT depends on the previous Z's and the current and previous X. So this is what is shown in the first diagram with the black arrows. Of course, as for VAEs, the posterior distribution is approximated by a normal distribution whose parameters are computed from HT and the current XT. As a reminder, HT encoded all the previous latent codes and observations. So in here, in VRNN, the HT in the inference model is exactly the same, meaning that it shares the parameters with the HT of the generative model. This is again an implementation choice, and we could have chosen otherwise. The drawback of choosing this factorization the one in the first equation, is that it does not follow the structure of the same posterior. So if you compute the posterior distribution of the latent codes given the observations, you end up with a distribution that depends, a distribution on Z that depends not only on the previous Z and the previous and current observations, but also on the future observations. So the dependencies on the future observations are missing, and this is why we put them in gold in the figure. In other words, there should have been in the implementation some sort of bidirectional RNN, or at least some sort of backwards RNN that would take into account the future observations as well. When it comes to the lower bound, there is nothing complicated, just a little bit tedious. We write the reconstruction term, which is in the first line, and also the regularization term that you can see in the second line. We have encountered these difficulties in the previous DVAE models. So while the KL divergence can be computed analytically, the expectations cannot be computed analytically and have to be approximated by Monte Carlo estimates. This has to be done in a recursive way, and of course using the reparameterization tick. By using all these, the resulting expression of the variational lower bound is differentiable with respect to both the parameters of the generative network and of the inference network. So as we have said, variational recurrent neural networks have the richest dependency structure. And another way to say that is that there is no simplification with regards to the general DVAE equation. As we have already said before, DVAEs can be implemented in many ways. This is also the case of VRNN. And in the original paper, the authors take some choices in the sense that they use a unique recurrent neural network that is shared by the two generative modules, meaning of Z and X, but also by the inference network. We will now discuss other DVAE models, but we will present them a bit more quickly. And in particular, we will not detail the variational lower bound, because its derivation and optimization follows the same principle as the ones in VRNN. If you want to have all these details, you can go and check our review paper that is on arXiv. The first model we would like to discuss is the Kalman Variational Autoencoder, or KVAE. This is a NeurIPS 2017 paper. The Kalman Variational Autoencoder is a combination of a Kalman, or a state space model, and a variational autoencoder. In very short, we have the latent code Z that follows a first order Markov chain, as in the Kalman filter. This Z generates a variable A, which would be the observation of the Kalman filter. And this dependence between Z and A is linear Gaussian. The emission variable A of the Kalman filter, or the linear Gaussian state space model, becomes now the latent code of a decoder of the VAE, and is therefore used to generate the parameters of the distribution of X, as you can see in the equations. So we start from the last equation. Z follows the first order Markov chain. A is generated from Z following a linear Gaussian state space model, and finally X is generated from A using a nonlinear generative network. This is the generative model of the KVAE. Regarding the inference model of the KVAE, we split the joint distribution of the state sequence and the latent code sequence, so A and Z, as the product of two distributions, the one of Z given A and the one of A given X. While Z given A is computed with the standard Kalman filter formulation, the one of A given X is computed using the encoder of the associated variational autoencoder. In this case, differently from VRNN, the inference model follows the form of the exact posterior distribution. In practice, and this is not detailed here, KVAE at inference time is using a weighted Kalman filter, and the weights of this Kalman filter are computed by a neural network. So it is a bit more complex than what we have described here. And once again, if you want to check the details, you can either go to the original paper or to our review paper. Another model we would like to discuss is the stochastic recurrent neural network, which is a NeurIPS 2016 paper. Even though this has the same name as STORN, the acronym is different. It's SRNN. So you have to be careful. These are two different models, and you can distinguish them not by the name, only by the acronym. The generative model of the SRNN is shown here on the diagram and as well as on the equation, and it is less complex than the one of the VRNN. Indeed, if you take a look to the probability of the observation, you can see it depends on the previous observations, but only on the current latent code, while for a VRNN, it depended also on the previous latent codes. Regarding the distribution of the current latent code, it depends on the previous observations, but only on the previous latent code, not on all previous latent codes, as in VRNN. Both the distribution of the observation of the latent code are assumed to be normal distributions. The one on the observations depends on HT, which is a recurrent variable encoding all the previous observations, and on the current latent code. And the one on the current latent code depends on the very same HT, that once again encodes the information of all previous observations, and on the previous latent code. Once again, this is an implementation choice, because we are using the very same RNN with internal state HT to encode the information for the generation of ZT and of XT. And this is the same as in VRNN. Regarding the inference model, the exact dependencies are shown here on the equation and on the diagram. The posterior distribution of ZT depends on the previous latent code, ZT-1, and on all observations x from 1 to t. Of course, Q phi is assumed to be a normal distribution, whose parameters depend on ZT-1, but also on a backward RNN, which is computed not only using the current observation, but also the current hidden state HT. So, as you can see on the diagram, HT is a forward RNN, GT is a backward RNN, and therefore GT encodes the information of all the observations that are needed jointly with ZT-1 to compute the parameters of the approximate posterior distribution of ZT. In this way, the authors implemented a mechanism that follows the structure of the exact posterior distribution. Another model that we would like to discuss is the recurrent variational autoencoder, or RVAE. The generative model of RVAE is simpler than the one of SRNN. Indeed, the prior distribution of the latent codes is a standard multivariate normal distribution and is independent per each latent code. So in a way, this prior is similar to the one of the variational autoencoders. However, when it comes to the likelihood or the generation of XT, this one depends on all the previous latent codes, Z1 to T. More precisely, the generative model of XT is a normal distribution whose parameters are computed from a recurrent variable HT that encodes all the previous and current latent codes. You can see how this is implemented in the diagram on the right part of the slide. Regarding the inference model, the exact distribution follows the equation that you have on the slide as well as the diagram. So in a way, ZT, the posterior distribution of ZT depends on all the previous codes and all the future observations. Of course, the inference model is assumed to be a normal distribution whose parameters depend on a forward recurrency and a backward recurrency. The forward recurrency encodes the previous latent codes, and the backward recurrency encodes the future observations. In this way, we can account for all the dependencies of the exact posterior. We remark that the forward recurrency of the inference model is different than the one of the generative model. This is also an implementation choice. This recurrent variational autoencoder has a non-causal version in which the generation of XT depends not only on the past codes but also on the future codes. In this case, the generative model is implemented with a bidirectional recurrent neural network on ZT. And the inference model, the exact inference model, depends not only on the future observations but also on the past observations. And therefore, to implement that, we need a forward recurrency on ZT and a bidirectional recurrency on the observations. To our knowledge, and very differently from all the models that we have presented so far, this is the first non-causal DVAE generative model that is found in the literature. The next model we would like to discuss is the disentangled sequential autoencoder that was presented at ICML in 2018. The disentangled sequential autoencoder, as its name indicates, is very similar to a state space model, but it is enriched with a sequence level variable, V, that is assumed to encode properties that are constant all along the sequence, and therefore it should allow to disentangle those static properties from those dynamic properties that should now be encoded by Z. The generative model is quite similar to to the one of a higher order state space model. So V has its own prior. The distribution, the observation, the likelihood depends on the current latent vector and on the sequence variable V, and the latent code depends on all previous latent codes. Of course, all these distributions are chosen to be normal distributions, and their parameters are encoded by different networks, or in the case of the parameters of X, there is no need for a recurrency because it depends only on ZT and V. In the case of Z, because it has to take into account all the previous Zs, then it's implemented through a recurrency that is denoted here by HT. Regarding the inference model, in the original paper there are two versions. We here describe the full version. The inference model is quite complex, as you can see on the slide. And this is because both the inference model of V and the inference model of ZT depend on the entire set of observations X from 1 to D. In addition, ZT depends also on V. So, this is why we need a forward and backward recurrency on the observations to estimate the parameters, the posterior parameters of V, and we need a different forward-backward recurrency on the observations that is influenced by V as well, to obtain the parameters of the approximate posterior distribution of ZT. However, this inference model does not follow the exact posterior. Indeed, if you compute the exact posterior distribution, you would see that while for V the proposed approximation corresponds to the structure, meaning that V depends indeed on all the observations, the posterior approximation of Z should depend, in addition to V and the future observations, should also depend on the past latent codes. However, it should not depend on the previous observations. So this is why in the figure here in the diagram on the right, on the bottom right, you have in yellow the arrows that should have been there but are not in the proposed approximation, and in gray the arrows that should not be there but they are taken into account in the proposed approximation.
Okay, thank you, Xavi. We have almost finished our review of the DVAE literature, at least for the models that we wanted to detail. And before we go back to the general class of DVAE models, we can have a quick look at some other related works in the literature. We found out a series of works that are closely related to DKF-DMM and more generally to the deep state space model approach. For example, we can mention the latent linear dynamical systems and the structured VAE by Johnson and colleagues, the black box deep SSM of Archer and colleagues, then extended by Zhao and Park, the deep variational Bayesian filters by Karl and colleagues, and the disentangled SSM by Miladinovic and colleagues. Then we have a series of models that are more connected to Stone, VRNN, and SRNN, like the Variational Recurrent Autoencoder by Fabius and van Amersfoort, that was published in 2014 and was probably very inspiring for later works. We have the Factorized Hierarchical Variational Autoencoder by Su et al. We have the DRAW model, DRAW for Deep Recurrent Attentive Writer, by Gregor and colleagues, which models the generation process of an image. We have the Neural Adaptive Sequential Monte Carlo by Gu and al. We have the Recurrent SSM by Hafner et al. We also have some papers in a different spirit, for example, a mix of VAE and Gaussian processes in the GPVAE of Fortuin et al. And finally, we can also mention a series of works on disentangled temporal extensions of generative adversarial networks that are using the adversarial training methodology specific to GANs instead of the present VAE methodology. 4 of these 5 papers mentioned here use these models for separating content and motion in videos, with some impressive results on synthetic videos. And the 5th paper considers an application in speech synthesis. So this was a quite short complementary tour of the literature. It would be a bit tedious to provide more details here. And for more information on related works, please see our DVAE review paper. Okay, a few slides ago, we have just had a glimpse on the general class of DVAE models. Now it is time to present and discuss this class more thoroughly. So, first of all, we recall here the general DVAE equation. The parameters of the generative distribution p theta x and p theta z are provided by feed-forward deep neural networks, or recurrent neural networks, or combinations of them. These networks take the conditioning variable as input. We recall that the most general and richer dependencies are a dependency of both zt and xt on all previous observed vectors and all previous latent vectors, while xt also depends on the current latent vector zt. This corresponds to some causal sequential sampling. For example, we would first sample z1 and then sample x1 from z1 and then sample z2 from z1 and x1 and so on.
The reformulation of the generative process in non-causal form is possible, but let us say that it is not really interesting. In practice, for real-world signals, we are mostly interested in, say, causally plausible data generation. In the literature, the causal form is predominant. We have seen that different DVAE models correspond to different simplifications of the dependencies in the two generative distributions, or no simplification at all, for instance, for VRNN. We recall that the presentation focused on Gaussian distribution for convenience, but in principle, both p theta x and p theta z can be chosen arbitrarily. P theta z being Gaussian is common practice, whereas the choice of p theta x depends on the nature of the data. Then, an important observation that we can make after our DVAE tour is that the presented DVAE models can be grouped into two main subfamilies. On the one hand, we have state space-like models, DKF-DMM, KVAE, DSAE, with an independent dynamical model in the sense that the dynamical model does not depend on xt, it separately models the evolution of the state sequence, and an instantaneous observation model. And on the other hand, we have predictive-like or autoregressive-like models, STORN, SRNN, VRNN, with more intricate cross-dependencies between variables, in particular xt-1 or x1 to t-1 is being used for the generation of xt and or for the generation of zt. Of course, we can expect those two kinds of model to behave a bit differently, and we will come back to that when presenting some experiments in part 4 of this tutorial. We can also list a certain number of bullet points regarding the inference model in DVAEs. First, in general, the approximate posterior distribution Q is a Gaussian. The parameters of this distribution are provided by feed-forward deep neural networks or recurrent neural networks or combinations of them. These networks take the conditioning variable as input. The second point is that there is a large variety of possible inference models in terms of variable dependencies.
There exists a methodology called d-separation to identify the form of the exact posterior distribution in terms of variable dependencies. We have introduced d-separation in the presentation when we presented the inference model of DKF-DMM, but we have not detailed this method. We just point those two references, and there are certainly many others. What is important here is that it makes sense to inspire from the structure of the exact posterior to design the inference model. The exact posterior is often a non-causal form, that is, it uses information from future observations because ZT participated to their generation. We have remarked that in the literature, the proposed inference models may or may not follow the form of the exact posterior distribution. We have remarked that in a general manner, in the earlier DVAE papers, the author did not care about this point, and in more recent papers, they did. So we can imagine that on the way, the DVAE practitioners have tended to realize that this was an important point. And indeed, in our experiments, we found out that it is better to do so. We will present some experimental results in part 4. But this is not always possible. For example, if one has to use a causal inference model for online applications, whereas the exact posterior is non-causal. The next very important point that we want to highlight is that there exists a variety of implementations, and this is true for both the generative model and the inference model. For example, different modules of the decoder may or may not share RNN internal state vectors, and thus parameters. Generation modules can even be shared by the encoder and the decoder. This is somehow recommended in the literature on structured or hierarchical VAEs. See those papers by Salimans, Sonderby and colleagues, or this tutorial paper by Kingma and Welling, the co-founders of the VAE. Neural network architectures may also vary a lot. We can have a simple multilayer perceptron to implement a first-order temporal dependency or any instantaneous mapping. We can have a basic single-layer RNN or a multi-layer RNN or an LSTM GRU network to implement long-term temporal dependencies. Hyperparameters tuning may also vary a lot. We can vary the number of layers and or the number of units, as is usual in deep learning. Unfortunately, we do not have time to consider extensively this kind of issue in this presentation, but at least it is important to mention it. The next point is about the variational lower bound that is used to train the DVAE models. One of the contributions of our DVAE review paper is that we present for the first time a general developed form of the VLB corresponding to the most general DVAE formulation. To do that, we start again from the generic compact expression of the VLB in the sequence modeling framework, as we did when we derived the VLB of the DKF-DMM model. And then we combine three things: the general equation of the DVAE generative model, the chain rule applied on the inference model, and finally, a new cascade rule, which is valid for any function of the latent vector sequence. And then we show that the VLB of the most general DVAE model can be expressed in this developed form, with a summation over the time frames of two terms that correspond to a reconstruction error over the observed data and a regularization error over the latent vectors, which ensures some kind of consistency between the generation and inference processes. Of course, this general VLB equation can be simplified depending on the chosen DVAE model. And in fact, in the previous slides, we have already seen the result for DKF, DMM, STORN, and VRNN. In its most general form, it is computed by replacing the expectations with Monte Carlo estimates obtained from recursive sampling of ZT. The resulting VLB is differentiable with respect to all neural networks parameters and can be maximized using stochastic gradient descent techniques. And finally, a remark. I have just mentioned that in this tutorial we have presented the particular form of the VLB for DNN, STORM, and VRNN, but not for KVAE, SRNN, RVAE, and DSAE. This was for concision. This information can be found in our DVAE review paper. To conclude on the DVAEs as a general class of models, I would like to take a different but somehow complementary point of view to derive an alternate definition of DVAEs. I would like here to take the Bayesian networks as a starting point. I do not have time to describe extensively the Bayesian networks here, but let us just say that a Bayesian network is a probabilistic model where the dependencies across the random variables are explicitly represented by PDF models and can be schematically represented using a directed acyclic graph. Basically, this means that there is no closed loop in the variable dependencies, in which case things would become much more intricate. Then we can easily define a dynamical Bayesian network, which is a Bayesian network with a dependency structure that repeats itself over time. Basically, this means that a variable xt would depend on a variable zt the same way as xt-1 would depend on zt-1. Then we can easily define a deep dynamical Bayesian network, which is a dynamical Bayesian network implemented with DNNs and RNNs. And now we can say that a DVAE is a mix of a deep dynamical Bayesian network and a variational autoencoder. More specifically, a DVAE is a deep dynamical Bayesian network that jointly models an observed vector sequence and a latent vector sequence, and that uses the VAE inference and training methodology. This means that we define an inference model, which is another deep dynamical Bayesian network, and we maximize the corresponding evidence law bound. Again, we give more details on this alternate definition in our DVAE review paper. This concludes our exploration of the DVAEs as a general class of models. In the next part of this tutorial, Simon and Xavi will illustrate the practical interest of DVAEs with some applications and experiments.